We're going to say a little bit more about Cantor sets. Let's recall some of the ideas from before. Say that we have the unit interval from 0 to 1. We'll remove the middle 1/3 of this set so that we have the union of two intervals from 0 to 1/3 and from 2/3 to 1. Next, we'll remove the relative middle 1/3 of this set. By relative middle 1/3, what I mean is that we want to remove from 1/9 to 2/9 and then from 7/9 to 8/9. You can see here in the diagram what we're doing. The solid bar at the top is the interval from 0 to 1. Just below that, you have the two solid bars. These will be the intervals from 0 to 1/3 and then from 2/3 to 1, and so on and so forth. Continuing in this fashion, we have a sequence of subsets, which we can write recursively in this way here. You'll notice that all that we're doing is removing the relative middle 1/3. There's a theorem that says that our limit consists of the set of real numbers x that can be written in a ternary expansion, a sum a sub k over 3 to the k, where each numerator a sub k is either 0 or 2. This limiting set is an uncountable set. We call this set the Cantor set, and the elements of this set are called Cantor numbers. Today we're going to discuss some generalizations, and we want to start by discussing the Smith-Volterra Cantor set. In all of this, recall that the German mathematician Georg Cantor was very interested in the ideas of set theory. He was actually building on the ideas of the English mathematician Henry John Smith and the Italian mathematician Vito Volterra. Cantor was working on all of this in 1883, although Smith had some ideas before in 1874 and Volterra soon after in 1881. Actually, the three of them considered a different set from the one we introduced before. Let's talk about what they did. Again, let's consider the closed interval from 0 to 1. We'll remove the middle 1/4 of this set. So now we have the interval from 0 to 3/8 and then 5/8 to 1. We'll remove the middle 1/16 of this set, not the relative 1/16, but the actual length 1/16. This means that we have four sets, from 0 to 5/32, 7/32 to 12/32, 20/32 to 25/32, and finally 27/32 to 1. Recursively, we'll let Cn plus 1 be that subset of Cn found by removing 1 over 4 to the n plus 1 from the remaining 2 to the n intervals. The remaining set C is called the Smith-Volterra Cantor set. But now, we've had these two constructions which seem to be similar, but still they're different. Today we're going to talk about the general philosophy and put all of this together into what we'll call thin Cantor sets and fat Cantor sets. There really isn't anything special about either removing a relative 1/3 of the intervals or an absolute 1 over 4 to the n of the intervals. So we're going to generalize and give a very general construction. But to do so, we need to make a crucial observation. Let's consider the following continuous functions t0 and t1. They're just linear polynomials. We notice that the images of the interval 0 to 1 are just subintervals. So for example, by looking at the first linear polynomial, t0 of x is 1/3 x, we find that the image of the interval from 0 to 1 is just the interval from 0 to 1/3. Similarly, by looking at the polynomial t1 of x is 2/3 plus 1/3 x, we see that the image of the interval from 0 to 1 is the interval from 2/3 to 1. We can now iterate and consider the image of t0 under t0 and t1 of these two from above. We'll see that if we take t0 and then compose it with t0, then we find the interval from 0 to 1/9. We can compose t0 and t1, we find the interval from 2/9 to 3/9, and so forth. Intuitively, t0 corresponds to taking the interval from 0 to 1 and moving it over to the left, whereas T1 says take the interval from 0 to 1 and move it over to the right. You can see literally how this works for the image of the interval 0 to 1 for T0, and similarly for T1. When we consider now the compositions, you can see how T0 circle T0 is at the very left, T0 circle T1 is not quite to the left, it's sort of to the right of the left part. T1 circle T0 is to the right, but is sort of to the left of the right part. And finally, T1 circle T1 is to the very right. It's all the way at the end, being the interval 8/9 to 1. Another way to say this is that we have the following sets. We'll write C1 as the union of the intervals from 0 to 1/3 and the interval 2/3 to 1 as just T0 of the interval 0 to 1 union T1 of the interval from 0 to 1. Similarly, we have an idea here for the union of the four intervals C2. We can write it in terms of T0 circle T0, T0 circle T1, and so forth. We're going to use all of this now to generalize. Let's consider a sequence epsilon1, epsilon2, epsilon n as a collection of real numbers between 0 and 1. We'll now write a sequence of continuous maps in terms of T0 and T1 as you see on your screen. Similar to what we did before, we have now these images where T0 to the n sort of looks like we're squishing everything to the left, and T1 to the n looks like we're squishing everything to the right. We can now consider the compositions of these, and we see that we actually have four intervals, just like what we would expect for the Cantor set. Using this, we're going to define the following sets. C0, of course, is the interval from 0 to 1. C1, of course, should be the image of T0 of this interval, union the image of T1 with this interval. And C2, very similarly, is what we get for these four. In general, we can write Cn as the following union. Some care needs to be explained here of the notation. It may help to look at the notation for C2. You'll see that we have T0 circle T0, but actually we have to be careful as to whether we're using epsilon1 or epsilon2 in our maps. Here, for Cn, we want to consider a union, but really we'd like to move over all possible sequences of zeros and ones. So here we actually do have a collection of n of these functions, t parentheses 1, t parentheses 2, but we're allowing ourselves to move back and forth between these subscripts, a sub n, either being 0 or 1. Think of this as for C0, we have just one interval. For C1, we have two intervals. For C2, we have four intervals. And in general, for Cn, we have 2 to the n intervals. These various intervals will keep track by the numbers 0 and 1. This will be the set sigma, which really is a sequence of zeros and ones. Here are some observations. C1 is that subset of C0 found by deleting an interval of length epsilon 1. This is the reason why we've introduced these parameters epsilon 1, epsilon 2, and so forth, that we'd actually like to keep track of the length of the intervals we're deleting. C sub 2 now is that subset of C sub 1 found by deleting two intervals of length 1 minus epsilon 1 over 2 times epsilon sub 2. And more generally, C sub n plus 1 is that subset of C sub n found by deleting 2 to the n intervals of length. Here we have a product over 1 minus epsilon sub m over 2, as m ranges from 1 to n, times epsilon sub n. Now, what we're going to do is put everything in one place and see what can we say about these sets. Again, we have a sequence, epsilon 1, epsilon 2, and so forth, where each epsilon is between 0 and 1. This tells us how much we're going to delete from each interval at every stage. We now have a sequence of maps, t sub 0 and t sub 1, that allows us to do the deleting, and we have our sets C sub n, which is just a collection of these 2 to the n subintervals. The main theorem here is that the limit, as we increase without bound, is an uncountable set. Here's the reason why. We have a surjective map onto the sequences of zeros and ones by deciding where our x in the set C lies. Remember that C sub n is the union over these 2 to the n intervals. Depending on which of these 2 to the n intervals we're in, we can then map that to a sequence of zeros and ones. But we've already seen that the collections of sequences of zeros and ones is an uncountable set. Let's end today's lesson by going over a couple of examples to explain how our two motivating examples fit into this construction. Say that we wish to construct the set C by removing a fixed percentage of every interval, where the percentage rho is some number between 0 and 1. For instance, the Cantor middle third set corresponds to removing the fixed percentage of 1/3. What we'll do is we'll choose epsilon 1, epsilon 2, epsilon n to be this fixed percentage rho. In this case, then Cn plus 1 is found from C sub n by deleting 2 to the n intervals of length 1 minus rho over 2 to the n times rho. This means the total amount remaining after we remove these various subintervals has length 0, as you can see here from the algebra on your screen. This makes sense for when rho is equal to 1/3. We're removing enough of the intervals that we're left with what's more or less called dust. This is why we call such a set C a thin Cantor set. Really, there's not much left over after we remove. But notice that this works for any fixed percentage rho. We don't need to choose rho is equal to 1/3, as in the Cantor middle third set. In fact, here are two explicit examples. When rho does equal to 1/3, we can explicitly write this thin Cantor set as, we mentioned earlier, the collection of real numbers x, which are sum a sub k over 3 to the k, where each numerator a sub k is either 0 or 2. Curiously, there's a similar result when rho is 8/10. Our thin Cantor set is the collection of real numbers x, which are a sum a sub k over 10 to the k, where our numerators a sub k are either 0 or 9. Now, let's say that we wish to construct our set C by removing an amount rho to the n, where our rho is between 0 and 1/3. We're going to remove this fixed amount at every stage Cn. For example, the Smith-Volterra Cantor set corresponds to rho is equal to 1/4. Now this is not relative, this is an actual amount that we're removing from our subintervals. We're going to choose epsilon 1 equals rho, epsilon sub 2 equals twice rho squared over 1 minus rho, and epsilon n as this funny formula here, such that the product that we get is actually rho to the n. Observe that each epsilon is between 0 and 1/3 as long as rho is between 0 and 1/3. This is part of the reason why we're choosing our rho to be between 0 and 1/3. In this case, the total amount that we find after removing each of these subintervals has positive length. That is, we actually don't remove everything. There are some items that are left over. Such a set is actually called the fat Cantor set. We'll definitely discuss more about this example in future lessons. Thanks for watching.